Okay, so we build out. Sometimes we may not need as much information as we build out, but we know that our area formula for circle is pi r squared. Circumference is c equals 2 pi r. Let's read the problem here. It says the radius of a circle is decreasing at a constant rate of 0.1 centimeters per second in terms of the circumference c. What is the rate of change of the area of the circle in square centimeters per second? So we're looking for the rate of change of the area of the circle. We're looking for the ADT. We know there's time involved. So let's build out our derivative. A becomes dAdt. Pi r squared becomes, we go through power rule, becomes 2 pi r. But then we're asking for r's derivative, so then we attach dr dt. It says the radius is decreasing at a constant rate of 0.1 centimeters per second. We see this is describing the radius, but it's not a static value. It's a moving value because we see the word rate, and the units of measure is centimeters per second. It's got to be something radius and time, involving radius and time. So then we know that's going to be dr dt. And also, we see the word decreasing. So we know we want that rate to be a negative value. So we can go ahead and plug in. Dr dt gets replaced with negative 0.1. And then they're asking to solve for dA dt in terms of circumference. And we know circumference is 2 pi r, and all of our answer choices in terms of c. So I can replace 2 pi r with c, and that gets us to the form that they want. Okay, number 2. Number 2, page 5, says the radius of a circle is increasing. At a certain instant, the rate of increase of the area of the circle is numerically equal to twice the rate of increase in the circumference. So again, we know that we're working with area and circumference of a circle. So I'm going to just go ahead and build out their derivatives and have everything in front of me. So again, we know dA dt is 2 pi r dr dt. Circumference dc dt is equal to 2 pi. Now r goes to 1, but we are asking for r's derivative, so we need to attach a dr dt. Okay, so they're asking, at what instant is the rate of increase in the area of the circle, we know that's dA dt, is numerically equal to twice the increase in the circumference. So the rate is dA dt equals twice the dc dt, right? Twice the rate of increase of circumference. So we're looking for when this equation is true, when dA dt is equal to twice dc dt. Okay, so we can just see what we can do to get these, what will allow for these two to equal each other. Well, we know dA dt is 2 pi r dr dt, so I'm going to go ahead and make that substitution. And then I can replace dc dt with 2 pi dr dt, and then there's 2 in front, so 2 pi. So it's asking what's the radius at that instant. So now we're just trying to solve for r. Well, we know dividing by dr dt, that will just cancel out. So I'm left with 2 pi r is equal to 4 pi. Now, if I solve for r, I can just divide both sides by 2 pi. That's just equal to 2. Okay, let's go to number 4. Number 4, the radius of a sphere is decreasing at a rate of 2 centimeters per second. At the instant when the radius of the sphere is 3 centimeters, what is the rate of change of the surface area of the sphere? So surface area is 4 pi r squared. So try this one, see if you can work your way to the end here. So start with s equals 4 pi r squared. So on the AP exam, they tend to not give you any formulas, but they will give you formulas of volume of shapes. So if it's surface area or volume of a sphere or of a cone or of a cylinder, those will be provided for you. Okay, if you're done with 4, let's go to 5. Okay, so number 4 real quick. S becomes ds dt, a pi r becomes, sorry, 4 pi r squared becomes a pi r dr dt. Dr dt is negative because radius is decreasing, so negative 2 centimeters per second, radius is 3 centimeters, and then we're just plugging in and solving for ds dt. Okay, here's page 6. This is a similar triangle problem, but this is very specific. We call this the shadow problem here. So number 6, a person whose height is 6 feet is walking away from the base of a street light along a straight path at a rate of 4 feet per second. If the height of the street light is 15 feet, what is the rate at which person's shadow is lengthening? So if you have the results of the street lamp creating the shadow, you can kind of see this triangle within a triangle forming. So I'm going to just draw another version of it, kind of just fill in the pieces here. So we know the person's height is 6 feet. We know the street lamp is 15 feet. And from here, we're just going to create X and Y. We can create proportions. We can say height of the small triangle is to the height of the large triangle as the base of the small triangle is to the base of the large triangle. So notice that we say it's y over x plus y and not x over x plus y. I know sometimes students want to say x over x plus y. It just feels more natural that, oh, x should come first, so that should be up top. But remember, well, the way that I drew it, x is not the full length of any base of a triangle. So we want to have y being the base of the small triangle, and then the x plus y being the base of the large triangle. And from here, we cross multiply. We do want to clean this up to the point where it's easy for us to find the derivative. I'm going to combine like terms. So relatively easy equation for us to find the derivative. 6x becomes 6 dx dt. And then 9y becomes 9 dy dt. Okay, and here are the 3 components of this problem. And we may not use all 3, but here are the 3 of them. The 3 are dx dt represents the rate of change of the person walking. Dy dt is the rate of change of the length of the shadow changing, increasing or decreasing. And then if I add the 2 rays together, that's going to be how fast the tip of the shadow is moving. So tip of the shadow is going to be moving on the ground based off of how fast the length of the shadows is changing and also how fast the person is walking. So both those rates will contribute to the tip of the shadow. So the tip of the shadow is going to move the fastest because it's getting impacted by 2 separate things. But this problem is only asking for the rate at which the person's length of the shadow is increasing. So we only have to look for dy dt. So dx dt is the rate at which person is walking, and he's walking away from the street lamp at a rate of 4 feet per second. So 4 will be your dx dt. And then you plug 4 into the derivative equation, and you solve for dy dt. Sorry, 4 into the dx dt, and you solve for dy dt, you get 24 over 9, and that's your answer. But if it was asking for how fast is the tip of the shadow increasing, then you would add these 2 rays together. The 8 thirds plus the 4, and that will get you your dx dt plus dy dt. But this problem is only asking us for dy dt. Okay, let's move on to derivative graphs or interpreting a derivative graph. So the graph of f is shown. Which of the following could be f prime? So I like to just go ahead and create my slope sine lines. And then from there, maybe I can have an idea what my f prime graph could look like. So this is my original function graph. So my original function graph is whatever you see is whatever you can expect. So let me call this -1 and 1 just to make it have some anchor points here. So we know that if for our slope sign line, our graph is going to be slope 0 at -1 and slope 0 at 1 based off of, I'm just going to have some numbers there. And then to the left of -1, my slope is obviously positive. Between -1 and 1, slope is negative. And then to the right of 1, positive slope. Concavity, it looks like the graph has a point of inflection at 0 because concave down followed by concave up. So now I want a derivative graph that's going to show these behaviors. So I'm going to create my own version of f prime and then see which could be a good fit. So remember, f prime graph above is positive slope, below is negative slope, and on the x-axis is slope 0. So I'm going to have my x-intercepts at -1 and 1. Those are my slope zeros. I want my slope to be positive to the left of -1. So that's going to have to be living in this region. It's going to have to come down. And then between -1 and 1, below the x-axis because of the negative slope. So it's going to have to go down, loop back up. And then to the right of 1, positive slope, so above the x-axis. Should make sense, right? This looks like a cubic function to me. Looks like an x cubed, so the derivative should be like something like x squared. And also point of inflection, second derivative connection here. 0 is a point of inflection. It must be a max or min of the f prime graph, which we see that's true. Concave down means my f prime graph is decreasing in slope, which it is, decreasing slope. And then concave up is positive slope. So that's going to be the best match with answer choice B. Okay, number 7. Let f be the function with a derivative given. Which of the following is the interval decreasing? So let's create our slope sign line, get all of our information, and then if we can create our slope sign line, our first derivative test, we should be able to look at our slope sign line and be able to have an idea where our graph is rising and falling. So we already have f prime, so we can just set f prime equal to 0. Find our critical points. I think it's best to, if I have a fraction, it's best to merge the fractions together. That way, critical points is easier to find because it's just be straightforward. Look at the numerator, look at the denominator, set them both equal to 0. But right now, it's kind of a mixed fraction here. So I'm going to find my common denominator. My common denominator is going to be x. I'm going to balance each fraction. The first fraction is missing an x, so multiply the top by x. The second fraction is already an x, so we keep that. Okay, so we set the numerator equal to 0. And then we also separately set the denominator equal to 0. So I have two critical points. The denominator gives me 0. The numerator gives me cube root of 2. Choose values in each subinterval to test. I can choose -1, I can choose 1, and then I can choose like 2 or 3. Plug them all into the derivative function to see what signs we get. We get negative 1 minus 2, that's negative. Negative over negative is positive. Plug 1 in, 1 minus 2 is negative. Negative over 1 is negative. And then plug 2 in, 8 minus 2 is positive. Positive over 2 is still positive. So decreasing is going to be on this interval here from 0 to cube root of 2. Okay, number 8, the graph of a twice differentiable function. So we're given a smooth curve here. Which of the following is true? So if you look at all these possibilities, these are all involving order pair, slope, or second derivative, or concavity at 1, right? And we just have to figure out, what's the order in terms of their value from decreasing to largest. So if we look at 1 here, let's see if we can look at the graph and be able to determine what each of those values could be. So f of 1 is just the order pair. So f of 1 is just what? What's the y value there? 0, okay. F prime of 1, this is asking for derivative, or in other words, slope. You may not know what the slope value here is, but in general, what's the slope going to be? Positive, right? You know it's going to be some positive value. And then second derivative is referring to concavity. You may not know the concavity value, but look at the shape of this graph here. This is clearly what? Concave down, which would mean what? You may not know the value, but you know it's going to have to be what? Negative, right? It has to be negative. So even though we don't know the values of these two, we know that negative is definitely smaller than positive. So we can order them that way. Negative is smallest, followed by 0, followed by positive. Let's look at number 10. Number 10 gives us f double prime, and it's asking for a point of inflection. So f double prime is equal to x times x plus 1 times x minus 1 squared. Then point of inflection is when x equals. So we know point of inflection comes from the second derivative. So we can set f double prime equal to 0. So critical points is x equals 0, x equals -1, and x equals 2. So is this my answer here? I still have to do what? Sign line. Because a critical point is not necessarily going to be a point of inflection. There has to be a change in signs, and we don't know that for sure until we actually test it. So this is a trouble spot. Sometimes on AP exam, some students feel, well, I found my critical point, so I'm just going to go ahead and circle that. But we have one more step to go. We have to look at our sign line. If there's no change in signs on either side of the critical point, it's not going to be a point of inflection. It's still a critical point, but it's not a point of inflection. So we're going to test them out. So -1, 0, 2. So I'll test it. I'll choose -2 as a test point here. I'll choose -1/2 as a test point. I'll choose 1 here, and I'll choose 3. And each of them can go into my second derivative. The nice thing about this last term, x minus 2 squared, is we know this is always positive. So don't have to test this value. Just have to test x and x plus 1. Because these are the only ones that could end up being negative. So negative times positive, which is positive. So that's concave up. -1/2, I get negative times positive. So only one negative. So concave down. Plug 1 in, positive, positive, positive. Plug 3 in, positive, positive, positive. So it looks like 2 is not going to be a point of inflection for us because there's no change in sign. So point of inflection only at -1 and then at 0. Let me skip to page 8. Oh, so first off, page 8 is a bunch of calculator questions. And these are just calculator in terms of sketching the graph and being able to look at the graph and being able to find critical points. So it's like looking at the f prime graph or f double prime graph, but instead of giving it to you on paper, they're asking you to graph it on a calculator and actually find those points yourself. We'll come back to this if we have time, but I want to go to page 13, 14. And the final miscellaneous topics are derivative of inverse at a point and linear approximation. So this is where we got to create the table, kind of make our way around that table. Let's do 1 or 2 examples of these so that I can refresh your memory with the process here. So the idea is that a function and its inverse will have certain relationships at the function level and also at the derivative level. At the function level, their order pairs will be flip-flopped. So if there's an xy on the inverse, then there's going to be a yx on the function. So order pair and function and inverse will always have flipped order of their x and y of their point. But then at those points, at those mixed points between a function and its inverse, their slopes will also have a relationship numerically. They're going to be reciprocals of each other. So there's a slope of 3 on one, there's will be a slope of 1/3. If there's a slope of 4/3 on one, there'll be a slope of 3/4. So I like to create a table as I build it. So here's my function. I'm given information at the inverse side, but I'm really going to be doing everything on the function side. We're not going to build the inverse. We're just going to do everything on the function side, and from here we'll make our conclusion based off of what we find on the function side. So I like to create a chart here to kind of organize my information. I know ultimately I'm looking for the slope of the inverse at 2. But I know that 2 is the x value of my inverse. So I'm going to create my order pair information here. But I also know that 2 is the y value of my function. It has to be, right? If they're inverses of each other. So I know that f of some x value must be equal to 2. So there's the order pair 2 comma something. And then on the function side, there must be an order pair something comma 2. So now I'm going to use this to help me figure out what that x value is going to be, because I'm trying to do everything on the function side. So I can set this equal to 2, and then try to work my way through, try to figure out what my x value is. So I'm going to try to bring everything over to one side. I like to do that to begin with. The 2's cancel out. So I think we can just go through a series of trial and error, guess and check, and it should be an easy number to find. If 0 doesn't work, then you can try 1. If 1 doesn't work, then you can try 2. It looks like 0 works, but 0 is not going to produce the derivative that we're expecting. So let me try 1. So 1 works. I think here we'll try 0 later, but I think both could work. So if I plug 1 in, I know my order pair is 1, 2, and 2, 1. So then if I can find f prime of 1, then we know that number will lead me to my answer that I'm looking for. So f prime of 1, let's first find f prime of x. F prime of x, the derivative is 3x squared minus 1. Now we can plug 1 in to find our slope, which is 2. So if my slope is 2, then the derivative of the inverse must be what? 1/2. Yeah, I don't think 0 works, so we have to choose the one that is going to lead us to an answer choice that's available. Okay, try 2. 2 and 3 should go a little faster because every information is there for you. You just have to kind of work your way around the chart. So try number 2. The important thing that students get stuck, well, the issue that students have is a lot of students want to put that 3 where the 3 is for the x. So just have to keep reminding yourself, okay, they're giving me really the y value of the function. Okay, if the x value that they're giving me is on the inverse side, then the number that I'm seeing is really the y value on the function side. So from here, we know, okay, I know at the very least, my y value of my function must be 3. And then we do have something that can help us with that. We know g of 3 equals 4. So that's going to force us to know, okay, my order pair on the function side must be 4, 3. So if I can find f prime of 4, then I know that number will lead me to what I'm looking for. So f prime of 4 is 3/2. So then simply 2/3. Okay, try number 3. Okay, number 4. F of x is 1 plus natural log of x. Find the derivative of inverse f2. We know 2 is the y value of the function that we're working on. So let's see if we can solve for x. Natural log of what value is equal to 1? And if you understand that it's e, that's great, but you can also raise both sides with e as the base and solve it that way. We know e and natural log goes away. I get x equals e to the first power, so x equals e. So there's my order pair, e comma 2, which must mean the inverse must have an order pair 2 comma e. So if I can find f prime of e, then I know that slope will lead me to my answer. So let's first find f prime of x first. 1 goes to 0, natural log of x, u prime over u, so just 1 over x. So f prime of e is just 1 over e. So if the slope is 1 over e, then the reciprocal on the inverse side, I know 1 over e will, on the inverse side, the slope must be the reciprocal, so e over 1, which is just e. Linear approximation. This is where we find our, I think we've seen a lot of this more recently because of all of FRQs that we've done. So we're going to build our tangent line equation. And then once we have our tangent line equation, we just plug the decimal into that tangent line equation. So let's just do it. Example 1, number 7 on page 14. Find your order pair, find your slope, build your point slope equation. And at the very end, you can plug that decimal in. Okay, page 15. So page 15 is your morning review. So tomorrow morning, I'll go over these pages as our final review before your part 1 multiple choice test. So again, topics, have them highlighted here. Limits and continuity, derivative, such as power rule, product rule, chain rule, quotient rule, implicit differentiation, related rates, derivative graph, curve sketching, linear approximation, EBQ, mean value, and all. Make sure you also look over your formula sheets. I think the formula sheet, I try to organize it in a way, and also we highlighted the concepts that you're going to see. So look over your rules, look over your formula, work through this. Page 5 through 8 and page 13 to 14, this is homework that'll be due on Wednesday. But tomorrow, tonight, just focus on preparing for your part 1 test. Bring your calculator, right? And I'll send a reminder this afternoon and tomorrow morning health session. I'll also send a Teams link tomorrow morning if you want to join their Teams for the morning health session. All right, come to your phone.
I think I have all the missing.
Okay, great.
Let's see. One through 4 into that.
Yeah, and I have that. Great, you're caught up. Thank you. Okay, great. I'll mark you down. Okay, great. All right, thank you. Yeah. Sure. Okay, great, thanks.
Sure. Then I'm like, well, it's not.
You have it? Or you don't? Give me a little.
Drastic change. So, Steve, I mean, wiggle.
Yeah, back at 6, right? Yeah, back at 6. Okay.